Hello everyone. Today we are doing a short video on vectors. So we're going to review what we've already learned about vectors so that we can be ready to continue learning about vectors in our next unit. So today we're starting off with the definition of vectors. Vectors represent both a magnitude and a direction. So a magnitude or distance and a direction. This is different from scalars. A lot of what we worked with so far in math are scalars, which are just numbers. In other words, you can think of them as just the magnitude part. And vectors are also different from rays, which just represent a direction. So rays end up going on forever in a direction. So no magnitude there. So vectors represent both a magnitude and direction. Negative vectors are the exact same magnitude, but the opposite direction. So to take a quick look at an example, if we had the vector v over here, and v is going up by 3, then negative v is going to be, we use a different color, negative v is going to be the exact same magnitude, 3, but going down. So this is negative v. So we can represent vectors with this notation here, both a magnitude and a direction. We can perform operations between vectors by adding them from what we call tip to tail. So looking at looking at adding vectors. We can add vectors by adding them tip to tail. And what this looks like is if we have a vector v, maybe v starts here at our origin and then goes to the right 4. And we have another vector u, and maybe u starts that same spot but goes up and to the right 2. Then in order to add v and u, what we need to do is take one of our vectors and move it so that the tail of that vector is now at the tip of the first vector. Finally, the sum of these vectors is the vector we end up with starting at that starting spot, going all the way to where we end up after adding them tip to tail. So this yellow vector here is v plus u, or u plus v. So we can add vectors by adding them tip to tail. When we subtract vectors, we are just adding the opposite of one of the vectors. So if we, for example, were to take our two vectors, v, and we wanted to subtract u, so again, v is just to the right 4. And we wanted to subtract u, what we would do is take u and flip it so it's in the opposite direction, and then add it tip to tail. So here v minus u is the same thing as v plus negative u. And negative u is down 2 to the right. Sorry, down 2 to the left 2. This is negative u. So we can take negative u and move it at it tip to tail to v. And then the corresponding vector, or the difference between the vectors, is going to be that final vector starting at that starting point and ending where, once we add them to tail, we end up. So here we have v minus u. And here the order matters. So this is how we can add and subtract vectors. Finally, we can multiply by a scalar by multiplying the magnitude. So if we had v and we wanted to multiply v by 2, then what we would end up doing is taking v, which has a magnitude of 4 going to the right. 2 times v is going to be the same direction going to the right, but instead of going to the right 4, we're actually going to the right 8. So this is 2v. So the direction stays the same, but the magnitude is multiplied by that scalar. We can represent vectors using algebraic notation, which makes it a little bit easier to work with vectors. For example, we could call a vector v and define it in terms of its components. A and b are the components of the vector. And a is going to be in the x direction, left and right. So a we'll sometimes call the x component, and then b is the y component. So for example, if we were to look at a vector b that starts here and goes maybe up 4 to the right 2. Here, v is equal to our x component is the direction that we travel in the x direction. Or sorry, the distance we travel in that direction, so 2. Our y component is the distance we travel in the y direction, up 4. So these are the components of this vector v. We say that 2 vectors are equal if their components are equal. So 2 vectors are equal if and only if, first defining 2 vectors, v equals we could say a1, b1, u is equal to a2, b2, and v is equal to u if and only if their components are equal. So if and only if a1 equals a2, sorry, and b1 equals b2. So these 2 are equal and these 2 are equal. Then we have equal vectors. We can write algebraic vectors as an equation. So for example, with v, we can rewrite it as a times I plus b times j, which is the same as writing it as a comma b. So we're writing the 2 components, and the I and the j just represent which direction or which component we're talking about. So a is in the x direction because it's multiplied by I, b is in the y direction multiplied by j. And this makes it a little bit easier to kind of like work with vectors algebraically. For example, if we were adding 2 vectors, v is maybe a1i plus b1i, and u is a2i plus b2i. To add v plus u, we would add the corresponding components, and we can think about these components kind of like as coefficients in front of I and in front of j. So v plus u is equal to a1 plus a2 I plus b1 plus b2 I. So adding the corresponding coefficients or components. It's the exact same idea if we subtract v and u. Here we have a1 minus a2 I plus b1 minus b2 j. Sorry, this should be a j because we're talking about the y direction or y components. Same thing over here. We should have j's in these two spots, j and j, for the y components. The magnitude of a vector can be represented or written as, we have two kind of like absolute value bars or vertical bars around our vector v. We can find the magnitude of the vector by taking the square root of a squared plus b squared. So kind of similar to our distance formula. And again, a and b are the two components for our vector v. All right, when we talk about a unit vector, we talk about a vector with magnitude equal to 1. If we want to find a unit vector, maybe u, in the direction of some given vector, v, for example, what we can do is take v and divide it by its magnitude. So the unit vector is equal to v divided by its magnitude. This equation also tells us that v can be written as the product of the magnitude of v times that unit vector, that direction. So this is the magnitude, here's the direction. So the unit vector can kind of represent a direction of a vector. Lastly, we can write vectors in terms of magnitude and direction. For example, if we have a vector v with magnitude here we have magnitude of v, and the direction is some angle alpha. And what this would look like is, for example, if we had a vector v here, alpha would be the angle here above the vertical, or sorry, the horizontal. And then the magnitude is the distance here. So magnitude of v, direction alpha. We can rewrite v as the magnitude of v times cosine of alpha times I plus sine alpha j. So this looks a little familiar. This is very similar to polar equations. We have the magnitude here, and then we have the x components and the y components in terms of alpha. All right, so we will look at a few more properties of vectors in the future, and we will continue to use this information that we learned about vectors in our previous units. So this all is important. A quick recap of what we talked about today. First, we define vectors as having a magnitude and a direction. Scalars are just numbers, arrays are just directions. A negative vector is just the opposite direction, but same magnitude. We can add vectors tip to tail, so lining them up tip to tail, and we can subtract vectors by treating them as addition of opposite vectors. Scalar multiplication is just multiplying the magnitude. Algebraic vectors can be written as two components, a and b, as we see here. Two vectors are equal if and only if their components are equal. We can write vectors algebraically using I and j, and then we can use those to add and subtract vectors. We can also find the magnitude using those components, a and b. The unit vector has a magnitude of 1. We can use this equation to find the unit vector in the direction of v. We can also write v in terms of the direction the unit vector is going in and its magnitude. Finally, we can write a vector in terms of magnitude and direction by using this equation here, magnitude times cosine alpha I plus sine alpha j.